until 4:30.
4:30. Okay, cool.
And we're watching for us to get on TV here, and then we know we've started. And there we go. All right, thank you all for coming today. I'm very happy to host John Nickolls from NVIDIA. John's the Director of Architecture for GPU Computing, and he's one of the key guys that did the design of the G80 that we've talked about in class, and it's the things that have followed it and the things that will follow it. So very grateful to have him up here this afternoon, meet a number of grad students and faculty, and let's make sure to ask him some good questions as he speaks. So thanks, John.
Thank you, John. Let me get this thing on here. Okay, so John said it would be interesting to talk a little bit about why we made some of these design decisions. So I thought, since I didn't really know what you were going to ask, I'll just walk through and describe a little bit about what we're doing on GPU computing today at NVIDIA. And please interact and ask questions, and that's where the why part will come out, okay? So I'm going to talk a little bit about what we mean by visual computing, and then I'll talk a little bit about the scalable programming model that's represented inside of CUDA, the programming model of CUDA, and use that to motivate some of the ideas that are in the architecture that we call Tesla. Tesla it's kind of a funny thing. We had an internal code name for the G80 architecture. It was called the Tesla architecture. We usually name internal projects after physicists and engineers and such. And long after that project was done and the chips were out there and so forth, we started making a computing product, and the marketing folks were looking for a good product name, and they ended up picking Tesla as their product name, and we said, oh, that's what we call it too. And they had no idea it was actually two totally independent evolution paths there. Well, he was a pretty cool engineer, I got to say. Let's see, and then I have a few examples if we have time to show some CUDA programs, but you guys are probably already more advanced than that anyway. And then a few applications that I thought might be kind of motivating or inspiring that we think are pretty fun to look at. So visual computing. So we're seeing this sort of convergence, if you will, between computing and graphics and interaction. And if you think really about what is a video game, it's really a real-time visual computing application. It's sort of the prototype of what do we mean by mixing graphics and computing so that you can interact, in real time visually with things that are computed inside of some piece of hardware. So the cool thing about it is that it's all very parallel. Graphics is highly parallel today, and computing on a GPU is highly parallel. So to me, the thing that's similar about both of them is that they're both massively parallel. They use lots and lots of threads, and that's the similar part of it. And the reason that's important when you think about GPU computing is that GPUs did not evolve initially to do computing. They evolved to draw pictures, and they evolved to do picture drawing in real time at a good interactive rate so that you could play games. I mean, let's face it, they're the main market that pulls the GPU architecture along is video games. Almost everything we put into a GPU today owes its existence to some feature or some attribute of a video game. If it's good for the hottest game today, then it's got to be good for the GPU. So that's what first and foremost determines what goes into the architecture of a GPU. And when we first set out to go do parallel computing on a GPU, we had to live with that legacy, if you will. In other words, first rule is don't mess up the graphics. You got to keep all those things that
work inside the GPU to draw pictures fast, they have to stay there.
So
Yeah.
What did you think was the hardest thing? Like what handcuffed you the most out of graphics when you were doing parallel compute?
The thing that's handcuffs you the most is probably the fact that most of the people designing a GPU don't know anything about computing. They only know about graphics. And the other sort of flip side of that coin is that all the economics, at least early on, all the economics were driven by the economics and the business of making successful graphics processors. And so when you propose to add something which is just there for computing, it gets frowned upon, right? It's just a cost, it's a burden, it adds area, it adds power, it adds complexity that people don't want. So you have to argue for every little thing that's different than graphics. So what that pushes you to do is figure out how do you make something in a processor do both graphics and computing, because then you don't have to argue about it. That make sense? So CUDA is a good programming model just because it's relatively simple and it seems to be relatively close to the GPU hardware that we've built. But it's inspired a couple other programming models, and I'm sure more will come. Apple, as you know, is developing this language called OpenCL, which is essentially derived directly from CUDA. And we have a version of it that's running today on Linux and Windows based on CUDA. And Microsoft has developed a new computing shader, they call it, for DX11, which will come out, I don't know, I'm not sure when Microsoft's going to come out with that, but it'll be eventually. But it's very similar to CUDA in spirit as well. Yep.
As far as that, do you foresee one overtaking the other, or do you think they both coexist somehow?
We'd like to see them all coexisting. I mean, from our perspective, all of these are good. They all help people use GPUs to do more stuff. They all make the GPU more useful. I think the biggest thing that we see is that parallelism is still scaling pretty fast. The device counts are still doubling every 18 to 24 months. So Moore's law is still pretty much well and alive. It's slowed down a little bit. The traditional Moore's law says that you can make a denser, more transistor count, more device count thing at a given cost every so many months. And that's still happening. May run out of gas here one of these days, but we haven't gotten there yet. And so what that tends to mean is that because individual processor cores are not particularly getting that much faster, it tends to mean that the number of processor cores is what's increasing. And you can see that in particular on the GPU side. So what that means from a software perspective is, how the heck do you use all that parallelism? I'd say the biggest problem we see in people trying to, for example, write CUDA programs or OpenCL programs is they start off and at first blush they just don't have anywhere near enough parallelism, just not even close. And let me show you why. Here's a little GPU. Okay, this has has 4 SM processors. Each SM has 8 scalar processor cores in it, so that's 32 cores altogether. That's a small GPU, but some of the laptops we sell today have half that much. So in each of those cores is multi-threaded. Each of those SP cores runs 96 threads. Okay, so now you're talking, a fair amount of parallel thread activity, right? Just to fill up one of these little puppies here, you need, 3,000 threads, something like that. Okay, and if you want to fill up a GTX 280 with 240 cores in it, you probably need 20,000 threads, maybe more. Okay, so if you have figured out how to make your problem 4-way parallel, that's pretty cool, but you're not anywhere near at the point of filling up a GPU. So the real essence of the problem in using a GPU that's this parallel is how in the heck do you come up with not just 240 cores worth of parallelism, but 20,000 threads worth of parallelism. And we see these numbers continuing to increase, sad to say, because that's easier. It's easier to increase the thread count and the core count than it is to increase anything else. So it puts a real challenge and a real burden in some sense on applications on how the heck do you use all that parallelism. So the problems that we see that fit well today on GPUs are those that are essentially data parallel, where we assign one thread to produce one piece of data, like one element of an array or one pixel in an image. And that works pretty well. So data parallelism, we know how to scale, but the challenge is how do you write one program, whether it be a graphics program or a CUDA program or some other language program, how do you write one program that runs on this GPU and this one and ideally ran on a CPU too? Okay. Same source. Yeah.
So CUDA is a data parallel language.
Yes.
How does one go about implementing a hybrid of both task and data parallelism in something like CUDA?
Okay, so the question is, how do we integrate hybrid of task and data parallelism?
If I were to, in order to, load up this 240 core monster with sufficient work to keep it busy.
Yep.
Let's say that my data domain only covers half the cores, but I need to do two things to it. How in CUDA would I go about doing those two things? Where again, I got to do one thing first, then the other. That's
actually it's a problem for us today. It is feasible today to write a CUDA program that does two different things by just you just say, if I'm going to do problem A, I branch over here, and if I'm going to do problem B, I branch over there, and that works.
Well, even if they're
but today, for the most part, we tend to view these devices as a single application at a time kind of a device, and so it works perfectly well for big problems like, gee, I want to run a particular game. The game has no problem filling up all those cores and more, and the same goes for big data parallel computations. If I want to do, for example, protein folding or molecular dynamics simulations, I have no problems finding a big array full of data, and I just chop it up into little bitty elements and assign threads, and I have probably thousands-fold more parallelism than I can express at a given time instant in this.
Well, let's take the protein folding example. So you can examine, you can set up your combinatorial space in such a way that it fills this entire set of processors, and you run some optimization, and some of them are going to be duds, and some of them are going to be promising. So that's one phase of the algorithm. The next phase is you're going to take the good ones, and you're going to do some more stuff to them. And so that's it's multiple tasks, which is data parallel.
Yep.
So they're not completely separate, but
right.
So the question is, how does something like CUDA support that sort of realistic?
Yeah, today CUDA doesn't do a very good job of supporting that kind of thing because it's really aimed at describing one task at a time. But you could imagine, going forward in the future that you could imagine partitioning these GPUs into pieces and having task A running here and task B running there, for example. I think it's quite feasible, and it's not hard to imagine how you'd express it in a language like CUDA, where you'd say this is a particular task and that's a particular task. In CUDA today, there is a partitioning called streams. So you can talk about, here's a program for stream A, and here's a separate independent task, if you will, stream B. So there is a syntax and a mechanism to do that in CUDA today, but it doesn't actually run on the GPU today in two separate places at the same time.
Oh, I think if you use streams, you might be able. It might asynchronously launch the second stream before the first stream is finished.
You can, yeah, but it's not as easy to do what he's looking for true. Can I run, say, 10 different tasks in here in parallel and fill up the machine with different tasks? And
can you just switch on
but we're not there yet today.
But like you said earlier, you could switch on the block ID or something and have have some blocks run one code and some blocks run another code.
Yeah, there is a way to do it. I mean, if you want to partition manually yourself, partition your CUDA program into the A blocks and the B blocks, and you branch on your block ID number, and certainly there's no reason you can't do that. I guess the only point of this slide was really to think about scalability up front, and the point is that when you write a program for a graphics program for a GPU, you don't know at the time you write the program how big a GPU the program is going to run on, because when you go to the store or you download a game, you expect that game to just work, right? And if you buy a bigger, faster GPU tomorrow, you expect it to just work, but faster, okay? So we'd like to have the same thing happen for computing, right? If I write a computing program and I say, oh, I want it to happen faster, and I'm running on this GPU right now, and then I go buy a bigger GPU and I say, gee, I want it to run faster. I don't want to rewrite the program. I just want to take the same old source code or even the same compiled binary. Okay, so one of the cool things about CUDA today is that you can literally do that. Take a binary of CUDA and run it on all these different sizes, and it's the same program. It just runs faster when there's more parallelism available, assuming your problem is big enough. So you guys know about CUDA a little bit, but basically it's just C. So you write a program for one thread, and then you describe how to instantiate that on many threads. And it's familiar because most people know how to write C programs. And it's scalable because you can write this one program and run it on different sizes without recompiling. And we also have a little bit internal effort underway to make this work on CPUs, where we map CUDA threads onto vectors inside a CPU, whereas on GPUs we map CUDA threads really to a hardware individual GPU thread. So some of the sweet spots are, really big parallel applications with lots of arithmetic, dense linear algebra, differential equations, n-body codes, finite difference kinds of codes, and things that need lots of memory bandwidth. GPUs have typically an order of magnitude more memory bandwidth than a typical CPU, because that's the limiting factor in most games. So CUDA programs can take advantage of that extra memory bandwidth.
So can you comment on that just a little bit, like from an architectural level?
Yep.
Why don't I get that on? I mean, a lot of x86 codes are limited on memory bandwidth too.
Right.
You guys do special.
Okay. So you can see here that not only are we scaling the number of processors, but we're scaling the number of DRAM components, parts, and we're scaling the number of pins out to DRAM. Okay. So on a GTX 280, for example, there's 8 separate DRAM partitions. Each partition is 64 bits wide. So this physical DRAM is probably 2 or 4 physical DRAM parts. Okay, it's hard to get a DRAM part with more than 32 data bits of pins. So there's a lot of bandwidth here. So the aggregate bandwidth on a GTX 280 is, I forget, 150 gigabytes per second, something like that. CPUs just don't go that fast. Okay, number one. Number two,
It's a pin count issue?
It's where do you put your money, right? We spend a huge amount of money to buy the very fastest DRAMs. These are GDDR3 or GDDR5 DRAMs, and they're specifically designed to have high bandwidth and not that much capacity, whereas CPU DRAMs are typically designed for capacity first and speed second. So it's a physically different part, and then physically the number of pins here. This GPU chip has over 2,000 pins on the package. Okay, and there's probably, there's 512 data pins alone just getting to the DRAMs, okay, plus all the address and control pins. There's a lot of pins going out to DRAM. And then inside there's this interconnection network. You can think of it as like a big crossbar switch, but it's really a packet switch. It's routing packets. For example, if this processor here does a load instruction or a texture fetch, it has to route that texture fetch request or the load address fetch request down through an interconnect, through this interconnect, over to the particular L2 cache and DRAM controller that owns that address. And then it has to pick up the data and then route the packet back and return the data packet back up to the processor. Okay, so there's a big inside network there.
So if memory capacity is memory bandwidth is such a big issue, are you investigating alternate techniques to link the chip with the memory chip, like die bonding and those kind of things?
Sure. So we're in a commodity consumer business, and the main issue in packaging is cost. If we sell a GPU, let's say for $50, the actual cost of the components, including the printed circuit board and the GPU chip and the RAM chips and everything, has to be probably less than a third of that end user sale price in order to have a chance of making any money off of it. And the amount of money you make off is about that much, right? So even at, say, a $200 GPU, still doesn't leave you that much for fancy packaging. So today, the only packagings that you're going to see are things that are really high volume, low cost, easy to manufacture in high volumes and make them reliable. So yeah, packaging is improving, but it's a really slow process. It's not increasing anywhere near as fast as device count inside of chips is increasing. The packaging stuff is a very conservative business in comparison.
I'm curious, this interconnect network is a crossbar, or what kind of network it is?
It varies with the architecture. It logically looks like a crossbar, but it's actually typically not, in fact, a crossbar. Sometimes it's more like a mesh network, or sometimes it's like
the problem with
multi-stage.
Crossbar is if you add more and more multiprocessors, it's not scalable. The crossbar.
I'm sorry?
The scalability of crossbar is not good.
So crossbars, the question is about the scalability of crossbars. So crossbars can scale. It's just a question of how much area are you willing to spend. And what performance do you want out of it, right? So the whole area of interconnection networks within a chip is a really big topic for us. It's a very important topic. And currently all of our internal interconnects are focused around bandwidth. Okay, so we're trying to maximize the effective utilization of these very expensive physical pins between the GPU chip and the DRAM chips. So we try to maximize the pin efficiency on every one of those DRAMs. Okay, so we can talk more about applications, but the thing that's been fun, at least from my perspective, is when people first try out and write a CUDA program, they get pretty darn good results right out of the box. Sometimes they get, say 5x or 10x compared to their CPU code. And then when they start tuning it, they get even better. And some of these people have been able to get factors of over 100 speed up compared to a CPU on different kinds of applications. And if you want to see more about these, you can go look on the CUDA website. The other thing I think which has been kind of fun to watch here is because the GPU is not designed to do computing at the outset, but rather is designed for displaying pictures on your PC, and it's bought by people who just want to have a PC, or maybe they want to play games. These are pretty high volume processors. So when you suddenly add to this high volume processor the ability to do parallel computing, it really has enabled a lot of people to go and try out something which previously was just too darned expensive. When I was at Masspar Computer back in the late 1980s, we were really excited about selling the first 100 massively parallel machines, and the trouble was they cost $250,000 to $500,000 to $1 million a pop. So, hardly anybody got to go play with them. And the thing that's been exciting to watch about GPU computing is that you can go down to the local store and buy one and put it in your PC and do serious parallel computing for hardly anything. And the number of applications that people have come up with, just playing with it and doing research on it and writing papers about it is pretty astounding. I mean, you guys are doing stuff we never would have thought of, so that's what's fun to watch. So we estimate there's probably over 25,000 active CUDA developers right now, and that number seems to be growing pretty well. And a lot of research papers. We'd like to see some more. And
we'll do what we can.
And I think the most important thing is to teach classes in how to write parallel programs, do projects in how to write parallel programs, synthesize something. So you guys probably already know this, but I can zoom over. I don't know. Tell me how much do you guys know about CUDA, or should I review it briefly, or?
High level's good. One thing that I hope you'll talk about as you do this is sort of how much of this programming model comes from the software guys. So they said we'd like to put together this software model, and how much came from you as an architect.
Okay.
And how did you guys negotiate to make it do the things that it does?
Sure. So there were some clear-cut design goals up front, which was, first of all, CUDA had to have the same scalability attribute that graphics programs have, namely when a game company develops a game, they expect it to work on any size GPU. Just flat out, that's got to be that way. And we had the same goal so that software developers could go and write a CUDA-based program and expect it to run on any size GPU, no matter how little or how big, and it would just work. And I think one of the cool things we decided to do early on was to make all of our GPUs CUDA enabled. There was a lot of debate internally. Gee, this is really expensive to develop, and we should have all this stuff. We should charge extra money for it. And we finally convinced people. Said no, it's going to be much, much better if we can make this just really pervasive and make it available to anybody. And that's been, I think, a really smart decision, because just the synergy of having so many developers has been just tremendously stimulating. People are having fun playing with it. So the key was to make sure that this programming model would work on little bitty GPUs and really big ones, and that it would increase over time, because we expect that with Moore's Law we're going to see more and more threads and more cores over time. And we wanted something that was familiar. We actually did a couple of surveys. We went out and talked to potential customers and asked them, would you like a language like this, like a data parallel language, or something like Fortran, or something like C, or C per thread, or whatever. Almost universally, people wanted something that they were familiar with, so that's how we ended up with C. We think that the advantage of that is that it lets programmers focus on the algorithms, the parallelism, and not worry too much about learning some new language or some new semantic, some new syntax. And the other key thing is that because the free market makes heterogeneous systems, right? We're not a monopoly, and there's lots of different ways to make computers. So almost by definition, a PC is a heterogeneous system, because it's got pieces from different companies, different people who had different ideas about how to do stuff. So we felt it was really important that CUDA be able to handle the heterogeneity inherent in a PC, namely that there's a processor from a processor company, there's a GPU from a GPU company, and we have to be able to make those two play together. And I don't want to have to see all the ugly details in between. I would just want to write a C program, and I don't really care that part of the C program runs on the CPU using an x86 instruction set, let's say, and part of the C program runs on the GPU. Okay. I just want to know that, you know, if it's serial or scalar, then it's going to run on a good processor for serial and scalar stuff, and if it's parallel, it's going to run on a good processor for parallel stuff. So some of the key abstractions, these came about mainly because the GPU has so darn many threads. Why does the GPU have so many threads? Well, not too long ago, before there were shaders, right, GPUs were all hardware pipelines. So the invention of the programmable shader for graphics was really what caused all these threads to come into existence. And the model is very nice because it says one thread draws one pixel, or one thread draws one vertex. And so it's very fine grained, and each thread is independent, right? The thread that draws this pixel is totally independent from the thread which draws this pixel and this pixel and this pixel. And furthermore, I have lots and lots of pixels, and the pixel count is growing, and the number of pixels I have to draw is far larger than the screen pixel count, because I have to draw things to calculate shadows and lighting and so forth. So we have a zillion threads. So how do I manage this if I want to make a computing program? Well, in graphics I have different shader types. I have vertex shader threads and pixel shader threads, and now we have geometry shader threads. In CUDA, we didn't know what to do, so we invented this thing called a thread array or a thread block, and then it's really just a group of threads, but they run concurrently at the same time. And then we made a second tier level above that, which said, here's an array of blocks. And so we have this hierarchy of concurrent threads. So that was one key concept. And then because these threads are fundamentally asynchronous, we had to have some way to synchronize them. So we invented a series of synchronization primitives. And then so that they could communicate, we had to have some means either by interconnecting them or by having a shared memory. And we picked the shared memory because we knew we could get to it from C. So those are really the three main abstractions. So if you go look at this hierarchy of thread notions, a thread is just an ordinary thread. And some people have said, oh, it's not really a thread. No, actually it really is, at least in NVIDIA GPUs. A thread has its own program counter. It has its own registers, private registers. It has its own private local memory. It has its own context, if you will, state. Now, we do execute them in groups, and we have several layers or hierarchy of grouping. At the CUDA level, the next visible level of grouping is called a thread block or a thread array. And you, the programmer, declare how many threads you want to have in a thread block. But when we execute those in hardware, we try to execute as many of them as we can in parallel. And so in hardware, you'll see we have another in-between level of granularity called a warp, which I'll get to a little bit later. And then these blocks are grouped into grids. So a grid is what executes the same kernel function on every thread. And of course, each thread needs some kind of ID number, so we have a thread index and a block index. So those are really the basic essence things that we added so that we had some way to organize threads inside the GPU. Any questions about that? Yeah.
Say a thread has independent registers. We are used to hearing that a single SM has up 8,000 registers.
Yep.
And I'm just wondering how hard it is to construct such a big register file. Are they constructed as vector registers internally, or are they independent of each other?
So we'll get to that in a minute. Why don't you make sure I answer it? If I don't answer it, so I'm going to talk first about software motivation and then come back, and then we'll talk about hardware. Okay, so, but you're right, building a big register file with 8,000 or 16,000 registers is I mean, they look more like RAMs than they look like register files internally. So a thread is in CUDA, as we said, it has its own program counter, it has its own variables, thread state, thread ID, and so forth. But there's no assumption made about how it's scheduled. It's truly asynchronous in the CUDA model from all the other threads. Okay. So on the GPU, we map a CUDA thread to an actual hardware GPU thread. When we run CUDA on a CPU, we implement virtual threads. For example, we actually implement a whole thread block, typically as a single CPU thread. And then we use vector instructions like SSE vector instructions, where each lane now of a vector might be doing the work of a CUDA thread, virtual thread. So another way to think about this is that a thread is, well, so I missed that. Well, okay. So a thread block is like a virtualized processor, or really like a multiprocessor, because a thread block is a bunch of threads. You've declared as the programmer that you want to have, let's say, 100 threads in this thread block. So you can think of it as a virtualized multiprocessor with 100 processor cores in it. And you can think of them all as running in parallel. Okay. And the nice thing is that for every time you want to do a kernel function in CUDA, you can change your mind about how many threads are in a thread block and how many blocks are in a grid. So if you have step one of your algorithm needs this much parallelism and this kind of parallelism, you can declare your kernel to have that sort of parallelism. And then if the next step has a different shape or a different size, you're free to do that. So it's different than some previous sort of flat data parallel languages have been, which sort of gave you a fixed processor count and you were stuck with it. Here we're trying to use threads as a very fine-grained, plentiful concept. So you can think of a thread block as being an independent parallel task, or an independent task, in the sense that because each thread block runs on an independent physical processor, it's free really to go do its own code. So you were asking earlier, gee, can I run multiple tasks? Well, if you partition your tasks amongst thread blocks, then really there's no performance penalty to having every thread block do its own thing and act independently. It just has to look at its block ID and say, oh, I'm in block ID such and such, therefore I should be doing task such and such.
So a follow-up question then. Mm-hmm. Is there the semantics to have, let's say that there's two thread blocks, and you want to thread blocks A and B, and A needs to do some work, and then B is going to pick up the work that A finished and work on it for a while.
Yep.
What are the semantics for organizing that?
Okay, so today that's tricky in CUDA, and the reason is we want scalability. So this last bullet kind of gets at that, and I have another slide coming up after this. In CUDA today, we say that the blocks within a kernel have to be independent, and the reason is that allows us to scale on and run that same CUDA program on a processor which can only, let's say, sort of the rule is I have to be able to run a CUDA program on a single processor which can only run one block at a time, or I want to be able to run it on one of those big ones that can run, say, 100 blocks in parallel at the same time. So in order to be able to do the 100 blocks in parallel at the same time, the tasks have to be independent. And if you wanted to have a producer block and a consumer block, that presumes that they're both running concurrently. which may not be the case if I have too small of a machine, right? If my machine is not big enough to actually run the producer block and the consumer block at the same time, I'm kind of stuck, right? I got to have some kind of a buffer in between. So for today, at least in CUDA, we say that the whole kernel of all the blocks in that kernel, if I go back to this picture here, all the blocks in this kernel have to run to completion before I can use any of the output of this whole grid of blocks. So this could be a producer grid, and I could then, after the producer grid is done, I could have a consumer grid, and that's typically what we do.
Right. Okay, so, but then you said that there's no, as a programmer, you have to assume that there's no scheduling guarantees.
Correct. Well, we do guarantee that a grid, you can set a barrier between the completion of this grid and
okay.
the start of a dependent grid. So blocks must be independent in CUDA now. That doesn't say you can't. So you can write an illegal CUDA program where blocks are communicating with each other if you know how big your machine is. We don't encourage it because it's not portable, but has been done. So the way most CUDA programs do this is each kernel is run to completion before you start a dependent kernel. However, you can coordinate. In other words, if you use atomic operations, you can have two different kernels or two different blocks even within the same grid, updating shared locations using, for example, atomic add operations, which promise to do a read, modify, write on a given value atomically. So I'm sure some of you have seen this basic kernel before, but here's a vector addition kernel, and I just write code for one thread which says add A sub I and B sub I since I'm thread sub I. And since I'm thread sub I know I can safely write my result C sub I. And how do I compute I? I compute it as my thread ID number plus my block ID number times the number of threads per block. Okay, so that's sort of a global thread number within the grid. And then to launch that CUDA program, I just call the vector add function, and I instantiate n threads. And in this particular case, I instantiate the n threads as n over 256 blocks, where each block has 256 threads. So it's plain old vanilla C code. When I think about what happens in a given thread. And then here I have some magic angle bracket syntax which says, instantiate n of these threads and have them all in parallel. Okay, so that's the basic CUDA program there. Any questions about that one? Global means that this function is an entry point for a parallel kernel. And the arguments are just ordinary C arguments. And then we calculate the thread index, the global thread index in this case. This is what I would call a classical flat data parallel decomposition. So I've taken my array of data and assigned one thread to produce one element. So that thread really doesn't do very much work. It does one add, two loads, and one add, and one store. And this code, the main code, runs on the CPU. It's serial code. Okay. Now, to make all these threads synchronize, we use barrier synchronization because it's well known, it's easy to understand. And then in the GPU, we built special hardware to do barrier synchronization in one instruction. That took a little bit of trickery, but it turns out to be very important to have really fast barrier synchronization hardware because it happens so often. So CUDA programs do this call to sync threads over and over and over and over again. Every time you write something which is got to be seen by another thread, you've got to do a sync threads. Yeah.
Is there a graphics equivalent of sync threads?
Is there a graphics equivalent of sync threads? Nope. Yeah, graphics is different. Graphics is much more in order, right? When you draw stuff, we promise to draw it and update it in memory in the order you specified it. I mean, it's much more of a linear pipeline. And there's an implicit global barrier between kernels at the kernel level. So you were asking earlier about kinds of parallelism. I think of it this way: there's thread parallelism within, amongst all the threads. There's quite a bit of data parallelism, both at a fine grain within a block and at a coarse grain across blocks. And there's task parallelism in that, to the degree that you choose to use blocks to do different tasks with different kernels. And of course, inside the machine, there's of course instruction level parallelism and pipeline parallelism all over the place, but that's usually not too visible. So if you look at the memory model, the things that changed in the GPU, so the GPU already had threads, okay, and it already had registers per thread and per thread local memory. The thing which was new for computing was the notion of a thread block. This is a collection of threads that are guaranteed to run concurrently. So this is the one place that we said we promise these threads are running concurrently, all the threads of a given thread block, so that you can communicate among them. And then the means of communication is shared memory plus barriers. So that was probably the number one new thing. And then the number two new thing was the notion of taking the DRAM and viewing it as a big, flat global memory, whereas before in graphics, DRAM was viewed as textures and as render targets or frame buffers, right? So, whereas in CUDA, that DRAM is just a big pool of bytes, and you can load and store any byte you want to. So we had to add load and store instructions to the GPU, because previous to G80 and previous to CUDA, there were no load and store instructions. There was a texture read instruction, and there was a way to render output pixels. That was it. So there was no instruction that said store data register 3 at address in register 2. Okay. You're looking puzzled.
There's no memory hierarchy in terms of a cache in this memory model.
Well, this is a CUDA model, right? This is not a hardware model. Okay.
And the CUDA model, I mean,
this can be cached. Nothing preventing this from being cached.
It's not in G80.
It's not currently cached, no.
Okay. How come? Like, why did? I mean, you even have some cache on the chip.
Yeah.
Extra cache. So what made you guys think as designers, you know what, we're going to make all this, we're going to make the CUDA memory path uncached? So the reason that we don't cache stuff on load store instructions today is because if you look at the texture caches, they are GPU-style streaming caches. They're not aimed at reducing latency. If you look at a typical CPU cache, right, its goal is to reduce the average latency of a load. Okay. Whereas a GPU, a cache is designed to maximize the streaming throughput. And in fact, a texture cache, typically, the latency when you get a hit in a texture cache is exactly the same as if you get a miss. So the whole pipeline for texture fetches is designed to miss. The purpose of the cache is to maximize the value of the DRAM pin bandwidth and to take those few values that several different threads are asking for and provide them again without having to go back out to the DRAM. Okay, so. And that's not useful in general purpose compute?
Oh, it is, but if I were to put that texture cache in the middle of the load path, it would make the loads slower, not faster.
you're saying latency is more important in a compute path than a texture path?
I think it is, yeah. We wish we had lower latency all the time, but the way that graphics covers up these, so graphics fetches from texture memory have long latency, and the way they cover that up is with many threads. So unlike a CPU, early day CPU, right, you say load, and the whole CPU pipeline would stall until the load comes back. Okay, so if you implement a cache with a one-cycle hit, and you get a high percentage hit rate, that's cool, right? You do a load, and it hits in 1 clock, and it comes back, and you can use it. That's great. Then the caches got slower, and the load to use delays got longer, right? So then they said, gee, now I want to be able to do a load. I'm going to hoist that load up earlier in my program, and I'll start the load earlier, and it doesn't matter that it takes more cycles because I can have, say, 2 loads in flight or 3 or 4 loads in flight. Well, in a GPU, we can have hundreds and even thousands of loads in flight, and the reason is that we have to do that in order to cover the long latency. So the whole structure of a GPU is completely different because it's aimed at bandwidth and throughput, not at reduction of latency. So in the CUDA model, this is a software model, so there's no cache visible here at all. It doesn't prohibit a cache, but it presents some interesting problems, as we'll see. But the point I wanted to make here is in the CUDA model, when you execute kernel 0, let's say, this is a grid of thread blocks, they can read anywhere in global memory, they can write anywhere to global memory, and when they're all done writing their result, these are producers, let's say, they produce their result in the global memory. When they're done, then we have an implicit synchronization barrier prior to when I can start up any thread in kernel number 1, which is a consumer of that result. Because I don't know the order of execution here, and I don't know how to solve the problem of, which thread finished first, and, if I start this thread first, does it want a result from that thread, which is already done, or does it really want a result from this thread, which is still running? So we just put a complete global barrier here. So CUDA has a global barrier between dependent kernels, and that guarantees that you can always read the results of the previous kernel. Yeah?
So then what is the advantage of your guaranteeing that certain threads run concurrently if they can't do anything with each other anyway?
Okay, so we're talking here about the threads in this block, for example, cannot talk to the threads in this block because they don't know if they're running at the same time. But within a thread block, I guarantee that all of these threads within a thread block are running concurrently, and they can communicate with each other, for example, through the per block shared memory or through global memory. So it's kind of a hierarchy, if you will. We restrict communication so that the threads which are in the same multiprocessor, all these threads in a thread block run in the same multiprocessor, and they all actually talk to the same shared memory. So this is quick, low latency, localized, and we get good performance. Yeah. Okay. Let me skip through this. So people typically use the shared memory as like a scratch pad memory for communication among threads in the same thread block. So they typically use their thread ID number as some part of the addressing of an array, typically, so that they can write an array element which they know is their own, and then they have a barrier, sync threads, and then they can read a scratch value produced by a different thread in the same thread block. That's a very common paradigm. One of the problems with CUDA is that if I have CPU host memory and I start off on the CPU side in a sequential code, and I want to call a parallel kernel function over in the GPU, I have to get the data moved from CPU memory where it starts over into the GPU memory, the device memory. And we have a function called CUDA memcopy, which does all that. That's all fine, but frankly, it's a pain in the neck to have to call these copy functions. So it would be nice to get to the point where we had a single unified memory address space for this, but there's a little bit of difficulty in making that happen because we don't make the whole system. We just make part of it. So here's some CUDA memory copy calls. There's a CUDA malloc, CUDA free, etc. Okay. Yeah.
I know on earlier versions of CUDA this has been fixed, but there was a problem with the interop between OpenGL and CUDA. Like it would actually have to do a CUDA memcopy back and forth.
Mm-hmm.
You know, it did it underneath the hood. Do you know why that was problematic? What was causing that?
Don't remember. Sorry. I'll have to think about that one a little bit. No, don't remember that problem. Okay. You think it's fixed now?
I've heard of it.
Okay. Good. Okay, so let's go look inside of a GPU. So here's a Tesla T10 or a GTX GeForce 280. So it's this collection of processors and an interconnection network and a set of memory interfaces. Okay, and each processor is part of a multiprocessor, and the multiprocessor we call a streaming multiprocessor. And I don't know how much detail you guys want to go into on this. I guess this is what the class
What's
is.
inside a SP?
Or inside of an SM, or?
I think they know the pieces.
Okay.
But talk about them all in sequence, and I think we'd like to hear how you built what's inside an SP.
Okay. So let's see.
Can you point to pieces on that?
Sure. So here, okay, so there's 240 SP thread processors here, and that means there's 30 SM processors, and you can see there are 10 clusters. So here's a cluster. Okay, and the cluster has 3 SM multiprocessors in it. So there's 3 times 8 is 24. So there's 24 SPs basically in this region here.
So those registers in the middle stripe there?
Yep, register file.
And then the logic's on the outside?
Yeah, so each SP is kind of a stripe, a thin, skinny stripe this way.
Actually, going back.
Yeah.
Okay. Is it all graphics functionality in the big middle stripe?
No, that's those are memory partitions.
Okay.
From DRAM interfaces.
Okay. And then down the middle stripe.
Down the middle stripe. Those are parts. This is part of the SM, and there's actually some interconnection network in the middle here.
So, what fraction of this chip do you think is compute?
Die
area, just the picture that you show.
Compute only.
Yeah. But I mean, if I write a CUDA program,
Probably less than 1%. I mean,
is
specifically only for computing. Okay.
what fraction of the chip can I touch using CUDA only, no graphics?
Oh, probably 85%. The part that you can't get to is visible here. The part that's used only by graphics is the blending part of the raster operation unit. Okay, the texture L2 cache. There are some modes of the texture unit which are hard to get to from CUDA.
Rasterizer?
Yeah, the rasterizer is a teeny little bit, but yeah, there's no way to get to the rasterizer. Rasterizer knows how to turn polygons into pixels. Yep.
A question about the fast math instructions.
Okay.
Does the precision scale linearly with latency.
So does the precision scale linearly with latency?
Meaning the fast math are lower precision, but they're also lower latency.
Well, they're all pipelined, right? So, we pick a pipeline stage count that we think we can implement that doesn't, break the budget. If you take too many pipeline stages to do something, it's hard to get it to fit in with the rest of the processor. So, the way the approximations are done is they do table lookups to get initial seed values, and then they interpolate between adjacent table locations. So there's a linear interpolation going on in there. And those are just, simple multiply adds. So the number of pipe stages is fixed and predetermined, and then the size of the table is what gives you the precision. So really, it's more of an area versus accuracy and cost. It's a cost versus accuracy trade-off, and they're selected. The accuracy is selected to be good enough for graphics. Yep.
You just said that CUDA doesn't get access to some of the texture caching. Then why does CUDA have a differentiate between textures and global shared memory? Because there are CUDA textures inside the language.
So CUDA uses the texture cache for when you do a texture instruction. So I take it back. So it does use this texture cache when it's doing a texture instruction, but not all CUDA programs use textures. Most of them use loads.
Oh, I'm sorry. So are textures also stored on global memory, or are CUDA textures stored in a separate area that's faster?
Well, okay. So global memory is just a way to describe the DRAM. And textures are stored there too. So if you go out and look in the DRAM, there's a mixture of textures and render targets and load store data and program instructions and stacks, stack space, all that kind of stuff. So let's see. Let's jump over to. Okay, you want to talk about this multiprocessor. So we chose to group 8 processor cores into a little group we call a streaming multiprocessor, the SM processor. And the reason is that in graphics, we execute threads in parallel groups we call warps. Let me see if I can find a picture of a warp here. So here's a picture of a warp. Warp comes out of the weaving terminology. So in weaving, the warp is the set of parallel threads which emerge from the loom. Okay? And so a warp in this architecture is the group of parallel threads that execute the same instruction at a given time. So it's like a SIMD architecture in the sense that, in a SIMD vector architecture, you say, for vector add, and all the lanes of the vector get added. You say you add lanes from vector A to lanes from vector B, and they all, add up lane by lane. The difference here is we call this single instruction multi-threaded to distinguish the fact that each of these threads is actually independent. They all have their own program counter. They can all branch independently. And when you execute an instruction, you really think of this instruction as being interpreted individually by each of the threads. And the SIMD architecture says, I'm going to execute groups of threads. In our case, we execute 32 in parallel at a time. We start them off that way, and then to the degree that they decide to follow the same program execution path, then we can execute that group of 32 threads on the same instruction by just decoding that instruction once and broadcasting it to the all 32 threads. And they're more or less synchronous, but if one of them does a branch on a condition, which is different than other threads in the warp, then we say that the warp has diverged, and we typically then serialize. So, for example, we usually follow the taken branch path first. So let's say half of the threads in the warp decide to take the branch and half decide not to. Then we follow the execution path of the taken side of the branch until we get to a synchronization point. And then we pop a little token off the stack, and we go back and we execute the other side of the not taken side of the branch until we get to a synchronization point. And then now we pop another token, and both the sets of threads are back together, and we have a whole warp again. Okay, so the goal was to execute pixel shader threads and vertex shader threads in their most common case, which is they're all running more or less the same program code all the time, and they don't branch very often. When they do branch, we want the flexibility to be able to branch and go do different things. And when we do that, we might suffer, say, a 2-to-1 penalty, or whatever the sum of the taken path and the untaken path is, because you have to do both. Right? Some threads take this path and some take that, so the whole warp goes along for the ride on both paths. But the advantage is that it allows you to write a program where you just think of writing a single thread program, and the hardware automatically looks at all these decisions. It compares all the decisions made on a conditional branch across all 32 threads, and it says, gee, did everybody go the same way? If so, we're unanimous and we can go. No problem. If we're not, we have to diverge and push a token on the stack and remember where to come back to. Yep.
This looks like the same thing when you mask certain lanes in a vector processor to have them do different things. So how does the independence of a thread show up?
How does the independence of a thread show up? So essentially what you're saying is that if you had a predicated architecture or you had predication on vector lanes, yes, you could do the same thing. Okay. The place where it comes in and is sort of more visible is particularly in control flow and branching and looping. I mean, if I write a while loop, for example, the hardware automatically keeps tracks of which threads are, active at a given point, and I don't have to, think too hard about it. I mean, you're right, I could implement all this stuff as predication, but it's convenient and easy to write programs which have independent per thread behavior. And this came from graphics because in the graphics pixel shader model, you write a program for one pixel. And that pixel is implemented with one thread here. And so if you say do this or do that or branch or whatever, it just works out cleanly that way.
So you guys are kind of casting your, okay, so on next Thursday we're having somebody from Intel come.
Okay.
And the Thursday after that we're having a different person from Intel coming. They're going to tell us why what they're doing is much better than what you're doing.
Okay.
So I'd like you to tell the class why your approach is better than their approach. And maybe you can very quickly characterize their approach, because I haven't really done that in class yet.
Okay.
What do you think are the real differences?
See, I'm not really sure that I know what their approach is, but I can perhaps guess.
Okay. Well, based on what we saw at SIGGRAPH last summer. So so they have a much more software schedule against a hardware schedule that you guys have. They're doing rasterization in software and many more things. And I mean, it's a very software-oriented architecture compared to what you're doing.
So we do a lot of things in hardware because we have a large number of threads that we want to manage, and we want to manage them at low overhead. So all the scheduling of these warps is done in hardware. On every cycle, the scheduler picks a new warp to run. And if we have a multi-issue machine, which the GTX 280 is, it can actually pick 2 warps to run on any given cycle on different units. So the nice thing about that is that these warps are truly independent, right? Warp 8 represents a set of 32 independent threads. Warp 1 represents a different set of 32 independent threads. And so I can freely issue these 2 instructions without having to worry about the fact that they're in the pipeline at the same time. There's no guaranteed no dependencies within them or among them. And because it's happening every clock, it's hard to imagine how I would do this in software fast enough. So we do it in hardware, and we don't have any overhead, therefore, in doing these schedulings in hardware. And in a lot of pixel shader or graphics applications, the thread lifetime is very short. in many cases, a pixel shader thread might only run 10 or 20 instructions before it's done. Okay, so if I have to have some kind of software scheduling which is so low overhead that I can start a pixel shader thread and execute 20 instructions of work and then exit and schedule a new one, I don't know about you, but I don't know how to implement that in software. Okay. The other thing that we get out of this is because the scheduler is hardware, we also get hardware barrier synchronization. So when a thread block wants to do a barrier synchronization, it issues one instruction which says wait at the barrier. And basically, because the machine is sequentially executing warps, as soon as the last warp to hit the barrier arrives, it's just a handful of clocks before the first warp after the barrier can resume. Okay, so it's very quick. We try to get as close to 1 clock delay between completion of a barrier and resumption after the barrier as possible, which makes it possible to do very, very fine-grained parallel stuff. The other thing I would say is, let's see, what else would I say is different about this?
Is there a big scoreboard in there then? It's keeping track of all the dependencies.
Yeah, each thread has there's certainly a register dependency scoreboard, so when you issue an instruction which produces a result, it's produced several pipeline stage later, right? So the next sequential instruction in that thread can't issue until its source operand registers are available, so there's a register scoreboard mechanism for that. The other advantage to doing these warps is that because there's no relationship between the data in this warp and the data in this warp and the data in this warp, I don't need any I have plenty of time, I guess is what I say. Latency-wise, the latency between when this instruction executes for warp 8 and when the next instruction for warp 8 executes is a function of how many warps are there in the scheduler. And therefore, I can minimize the amount of hardware I need to support all that. I can just write results directly right back to the register file. I don't need any bypassing or forwarding networks for that.
So as long as warps are ready, it's just round robin.
Yep. So if we come back here, okay. So some of the things that were changed, I guess, is that so this is basically a scalar instruction set architecture, and I think you'll see when you compare it to the Intel thing that they're looking at a vector style architecture, and the way you think about those from a programming point of view are quite different, right? In a CUDA program, you can see it very clearly. You are writing just C code, and you write, A gets B plus C. And A, B, and C are just simple scalar, floating point, or integer variables. If you want to use a vector machine, you're going to have to figure out and express explicitly, okay, I know my vector is 8 elements or 16 elements or whatever it is, and I have to figure out how do I fill up those elements and how do I, issue. It's like an SSE instruction. How do I specify that I want to cause 8 or 16 or 32 elements worth of work in one instruction? Whereas in CUDA, I'm writing a program for one thread, okay, and then I'm separately aggregating a whole pile of threads, and I'm saying I'm going to do those in parallel because I know I can do them in parallel because they're independent. Whereas if I have to write a vector program I have to express much more parallelism within my source code because I've got to somehow describe the fact that I'm operating on a big vector. So we're hearing from many CUDA programmers that it's much easier to write code for one thread or code for one element than it is to write vector code. Sort of anecdotal, but Okay, you asked earlier about the register file. So you can see here, each of these SPs has 2,000 registers. Okay, so that's a big number, right? So that means there's 16,000 registers in an SM. That's implemented as a multi-bank RAM, basically a big SRAM. And because we're executing the same instruction on a warp of 32 threads, and because register numbers are fixed in the instruction, right? You say add R1, R2, R3, let's say. That means that you can broadcast the register number to all the thread lanes, right? It's like a SIMD. So that's like a SIMD vector internally, but you don't have to think of it as a SIMD vector as a programmer. I think that's the advantage here, is that here you have per thread individual description. You're thinking and describing what happens on a per thread basis. Hardware under the covers is doing all this SIMD stuff for you and all this vector stuff for you. And it's also comparing stuff. So when we do, for example, let's see, I think I have another slide coming up. Here we go. When we do a load or a store, we're going to imagine you have I say load R1 from address in R2 plus 4 bytes offset, okay? So this says every thread go out and, you pre-computed some address into R2, byte address, and you're going to load 32 bits into register 1, okay? But I have a warp of 32 threads, so that means I have, in the machine, I have 32 different R2 values, right? Who knows where they point? They might point all over the place. So the hardware does what we call coalescing. Here's a picture that shows 16 threads, not 32, but you get the idea. So I've shown here that the addresses point to word addresses in a given 64-byte memory block. And what the hardware does is it picks, let's say, thread 0. Says, all right, we're going to go access that memory block. And then it has a whole mess of comparators in hardware, and it looks at all the other addresses and say, anybody else want to go to the same memory block? If so, we coalesce you guys all together, and we go out and we make one request for that memory block. When it comes back, we distribute the answers to the threads that want it, and if there's anybody who didn't get satisfied with this memory block, we make a second request. Okay, and then we actually pipeline all those requests. So in the worst case, a warp of 32 threads will serialize out and request 32 different memory blocks if it's scattered all over the place. But if the programmer is smart and the programmer has, tried to group addresses nearby, then the hardware detects that automatically and it requests 1 or 2 or however many blocks there are that are unique. So again, when you write a program, this tends to have a very simple form, right? If you declare some array A of n and you access some A sub I value, a simple way to access that is to use your thread IDX, your thread number, as the index. Okay. When you do that, you're guaranteed to get an easy to coalesce pattern because thread 0 asks for, let's say, address 0 in the array, thread 1 asks for address 1 in the array, and so forth, and they all just fall into probably 1 or 2 memory blocks. So the hardware detects that automatically, but the nice thing is that if you want to write an arbitrary, crazy program, it works, it just runs slower. Okay, where if you contrast that with a typical vector architecture, either the vector load requires that you specify a perfectly aligned vector block, or it penalizes you somehow for specifying a misaligned vector block, or in the case of, say, a Cray-style vector load, you can create a bunch of individual, a vector register full of indices and a vector register full of data, and you can go out and do a scatter load, but I don't know to what extent, if any, they do coalescing. So this implements a Cray-style vector scatter-gather, but it optimizes the performance so that it minimizes the number of memory blocks that are transferred. So it converts thousands of little tiny fine-grained requests for 1 byte or 2 bytes or 4 bytes per thread into big, coherent, memory blocks that it can transfer quickly.
Any closing thoughts for us?
Any closing thoughts? Okay. Let's see. I just want to show you a couple of cool things here. Let's see. So we recently been doing some work on sparse matrix vector multiplication and getting some fun numbers out of those in terms of gigaflops compared to CPU numbers. We think it's looking pretty good. These are not very big compared to dense matrix multiply, but we think it's a nice existence proof for doing a hard problem like sparse matrix.
What's the difference between the two Tesla models there?
Same model.
It's the same model, it's different algorithm. So CSR is the compressed sparse row, and the hybrid is a hybrid of that and something else. I knew, right. So we're using this now for physics. So CUDA is implementing a physics modeling system for real-time games, and you can now get games that have physics stuff built into them, so you can blast apart stuff with your weapon, break it up into real bitty pieces. And then there's some new cool stuff. I don't know if you've seen these 3D glasses. Those are kind of fun. They're active shutter glasses, and they're wireless, and they receive an IR signal from your monitor, and all you need is a regular old, well, not quite regular old yet, but 120 hertz LCD monitor, and you can watch true stereo at 60 hertz per eye, or 120 hertz frame rate, and that's it.
When will the students be able to get the glasses to take exams with?
That's a good question, yeah.